Hi, I'm Steve Sandler, the Managing Director at Picotest. In today's video, I'm going to show you how to use a unique control loop stability tool that's now available for Cadence's PSpice simulator. Every power supply has at least one control loop, and every control loop requires a stability assessment. The need for assessment may be dictated by a corporate or government guideline, by a statement of work, or just because it's good engineering practice. Modern circuits are making this much more challenging, and that's what makes this video valuable. In many modern applications, power management ICs, or PMICs, are used to generate multiple power rails. This ST Microelectronics demo board is a good example. This PMIC includes 14 power rails. That includes 4 buck regulators, a switching boost regulator, 6 low dropout linear regulators, and a DDR termination regulator. There are 2 separate challenges to determining the stability of these 14 voltage regulator control loops. First, none of the 14 power rails provide access to their respective control loops for direct measurement. Second, the buck regulators in this PMIC and in most PMICs use adaptive, constant on-time control. Constant on-time provides excellent transient response, but it's neither linear nor time invariant, which are 2 necessary conditions for stability analysis using traditional Bode plots. Since we always have access to an output capacitor, I developed a fast, simple, and non-invasive stability measurement analysis tool, NISM for short, using the voltage regulator's output impedance. This NISM calculation is a popular function on many network analyzers, and as we'll show in this video, it's now available in PSpice. Here you can see the measured output impedance plot at one of the 6 LDO output caps in the PMIC. You can also see that NISM reports the phase margin stability of the control loop as 49 degrees. The control loop stability is computed directly from the impedance versus frequency data, and the only requirement is access to an output capacitor. This NISM stability analysis tool is now available for PSpice, and it's free. This is the focus of today's video. In this video, I'm going to show you how to use the non-invasive stability margin tool, or NISM, in PSpice to determine control loop stability. I'll show a little bit of theory about how NISM works, the functional limitations, and I'll share some of my best tips. At the end of the video, I'll show you where to download the project so you can use it as an example to evaluate your own circuits. The impedance data required for the NISM stability assessment can be obtained from either measurement or from simulation. For this video's PSpice example, we're going to use the Picotest LM20143 regulator demo board set. This demo board set is readily available, and it provides access for both traditional Bode plot gain phase data and also for the NISM-based output impedance data. These boards are also very simple to use, requiring only a USB cable for input power, and even the load resistors are included on board. And we know the right answer. So if you decide to try NISM measurements yourself, you'll know if you got the right answer. The examples shown here are for the LM20143 buck regulator with 2 different PCB decoupling designs. The one on the left has an impedance that's not flat. The data on the right is for a flat impedance design with no resonant impedance peaks. The PSpice NISM data plots show the impedance data on the left axis, as well as the calculated QTG parameter on the right axis. The impedance peaks occur at M1, and the QTG peaks occur at M2. The impedance peak is a local peak, so the NISM range measurement equation is used. If both the impedance and QTG peaks were global peaks, then the NISM measurement equation could be used as it uses the data at the global peaks. We'll need to identify a frequency range that contains both peaks when using the NISM range measurement equation. Good candidates are 30 kHz to 200 kHz for the non-flat design, and 30 kHz to 125 kHz for the flat design. The Nism range measurement equation results shown below have the non-flat design with a poor stability of 37-degree phase margin, and the flat design returns NAD, which means the stability is greater than 65 degrees. That's it. It's really quite simple to use. Let me show you a little bit about how NISM works and its benefits, and then I'll provide some tips on how to do a NISM stability assessment. NISM accurately determines the quality factor or QTG of the impedance by evaluating the first derivative or slope of the impedance phase versus frequency data. This information, along with the frequency shift between the impedance peak and the QTG peak, is used to mathematically separate the impedance into the voltage regulator's active output impedance and the fixed output capacitor impedance. With these known, the traditional oscillator theory minor loop gain assessment is used to accurately compute the stability margin. NISM is an exact solution for the stability margin, also known as the closest point to the singular instability at 1, 0 on a Nyquist circle. The NISM calculated stability margin is then transformed to the equivalent second-order phase margin as the resulting output. The step-load response, whether control loop is critically damped, overdamped, or underdamped, is also directly related to the stability margin. In my university research work, I compared a wide range of solutions using Bode plot simulations of a second-order control loop and the NISM solution, confirming the exactness of the solution. Simulation was used to provide noise-free data and to eliminate any small errors associated with interconnects and signal injection. A similar comparison between measured Bode plots and measured NISM measurements yielded consistent results within 1 degree. The most important tip for using the NISM stability assessment is to find the correct impedance peak and QTG peak. This is done by comparing the control loop powered on and power off impedances. The impedance peak caused by the output capacitor resonating with the control loop active output inductance is the correct peak, which is indicated here at M1. This peak is visible in the on state of the purple trace, but it disappears in the off state of the green trace. M2 is the location of the red trace QTG peak that's closest to the frequency of the impedance peak at M1. NISM can be applied to measurement data, to simulated data results using the Sandler state space voltage regulator model, and even to simulated data from simplified voltage regulator RL models. NISM also works on the input impedance of a voltage regulator. The input filter stability, often referred to as the Middlebrook criteria, like NISM, is a minor loop assessment, so NISM works there as well, and you don't need to separate the input filter from the VRM. The plot on the left shows an input filter design on the LM20143 regulator that has a high impedance at 1 kHz and a 35.5 degree stability. However, turning the regulator on with this input filter shows how the active negative input resistance of the regulator reduces the stability down to 18.5 degrees. The goal of a quality power delivery network is to achieve flat impedance. So how do we assess the stability when there's no peak? You pat yourself on the back because you did a great job. Your design is very stable. Some voltage regulators, for example, constant on-time converters, are not linear and time invariant. These are 2 prerequisites for Bode plot assessments. In these cases, Bode plots will not provide a reliable stability assessment. A closed-loop measurement will work, and NISM is a closed-loop measurement. Thus, NISM will work in these cases where the Bode plot will fail. One note. Bode plots for higher order converters like SAPIX will not correlate well with NISM. However, NISM is still a better assessment than the Bode plot. Measuring the output impedance when the power supply is powered on and off demonstrates which peak is the active resonance that needs to be assessed by NISM. The active resonance is only present when the power supply is powered on. The plot above shows an output impedance profile when a sample LDO application is powered on, green, and when the circuit is powered off, in red. This allows for the identification of which impedance peaks are active and which are passive. In this case, the impedance peak at around 50 kHz is assessed to determine the stability of the circuit. The corresponding QTG curve of the on-state impedance is shown in purple in the plot above. The impedance peak at 50 kHz corresponds to a QTG peak at the same frequency, and this yields a phase margin of 42.51 degrees. Correlation between phase margin and the impedance peaking in the closed-loop output impedance can be used to derive the phase margin of the control loop from one closed-loop output impedance measurement. In this video, I showed you how to use impedance to calculate voltage. Voltage regulator stability. I showed you how to use the NISM algorithm in Cadence PSpice. I also showed you some tips on using the regulator on and off states to find the active inductance peak of the regulator output impedance, and how NISM also works for the regulator input filter stability assessment. Remember that this unique NISM assessment does not require access to the voltage regulator's control loop. It works with constant on-time control loops where traditional Bode plots fail. It works with measured and simulation data, and is free for download to use with Cadence's PSpice. PSpice version 23.1 ships with NISM installed, but you can also download various examples by clicking on the link in the description of this video or by typing in the listed URLs.